The discovery. Before explaining what pulsars are, it is worth telling the story of how they were found, because it is one of the most remarkable moments in the history of science. In 1967, a Cambridge PhD student named Jocelyn Bell Burnell was analyzing data from a radio telescope she had helped build when she noticed a strange repeating signal, pulses of radio waves arriving with such clockwork precision that she and her supervisor initially thought they might be artificial. They nicknamed the source LGM1, Little Green Men 1, half joking, half genuinely uncertain. Further observations revealed more sources with identical behavior, ruling out an alien origin. What Bell had found was a new class of object that nobody had predicted and nobody had been looking for. Her supervisor, Anthony Hewish, later received a Nobel Prize for the discovery. Bell did not. The controversy over that decision has never fully gone away. What a pulsar actually is. Born from the death of a massive star in a supernova explosion, a pulsar is a neutron star, the collapsed core left behind after the outer layers are blasted away, that spins rapidly and emits beams of electromagnetic radiation from its magnetic poles. A neutron star packs between 1 and 3 times the mass of the Sun into a sphere roughly 20 kilometers across, making it so dense that a single teaspoon of its material would weigh about 10 million tons on Earth. The magnetic poles are almost never aligned with the rotational axis, so as the star spins, the beams sweep through space like a lighthouse, and every time one of those beams crosses Earth, we detect the pulse. The pulsar does not actually pulse. It's a steady beacon that appears to flash because of the geometry of its rotation relative to our position. Radio pulsars. The most common and best studied type, a rapidly spinning neutron star emitting beams of radio waves from its magnetic poles, detectable across vast distances by radio telescopes on Earth. Over 3,000 have been discovered so far, and astronomers estimate the Milky Way contains well over 100,000 of them, most of which we cannot detect because their beams never sweep across Earth. They are born spinning fast and slow down gradually over millions of years as they lose rotational energy, a process so predictable that measuring a radio pulsar's slowdown rate tells astronomers almost everything about its age and internal physics. The slowest known radio pulsar completes one rotation every 6.7 hours. The fastest completes 716 rotations every second. Both are neutron stars, they just exist at opposite ends of a pulsar's life story. Millisecond pulsars. Some pulsars that should have slowed to a stop long ago are instead spinning hundreds of times per second, and the reason is one of the most elegant stories in stellar physics. When a neutron star in a binary system begins accreting material from a companion star, that infalling matter carries angular momentum that spins the neutron star up to extraordinary speeds, a process astronomers call recycling. The result is a millisecond pulsar, an old neutron star given a second life by its companion, now spinning with a stability that rivals the best atomic clocks on Earth. Millisecond pulsars are so precise that networks of them, called pulsar timing arrays, are being used to detect gravitational waves passing through the galaxy, ripples in space-time so subtle they would be impossible to detect any other way. In 2023, multiple pulsar timing array collaborations around the world simultaneously announced the first detection of a gravitational wave background, a faint hum of space-time distortion permeating the entire universe, using nothing but the ticking of millisecond pulsars as their instrument. Magnetars. At the extreme end of the pulsar family sit magnetars, neutron stars with magnetic fields a trillion times stronger than Earth's and a quadrillion times stronger than a refrigerator magnet. They rotate more slowly than typical pulsars, and instead of being powered by their spin, they are powered by the catastrophic decay of their own magnetic field, releasing enormous bursts of X-rays and gamma rays in the process. A magnetar's magnetic field is so strong that if one existed at the distance of the moon, it would erase every credit card on Earth and disrupt the iron atoms in human blood from that distance. In December 2004, a magnetar called SGR-1806-20 released a burst of energy in just 0.2 of a second that was more powerful than anything our sun will produce in 100,000 years. The burst was so intense it partially ionized Earth's upper atmosphere from 50,000 light-years away. Magnetars are the most magnetically extreme objects in the known universe. If you're enjoying this video, hit the like button. We're aiming for 1,000 likes on this one, and every single one helps more people find this channel. And if you're not subscribed yet, hit that button and stick around. Now back to pulsars. X-ray pulsars. Rather than emitting radio waves, X-ray pulsars release their energy in high-energy X-rays, and most of them are powered not by rotation but by accretion, matter falling from a companion star onto the neutron star's surface. As the material spirals inward through the magnetic field, it is channeled to the magnetic poles, where it crashes onto the surface at a significant fraction of the speed of light, converting gravitational energy into intense X-ray emission in hotspots that rotate in and out of view with each spin. Some X-ray pulsars spin spin extraordinarily fast. Accreting millisecond X-ray pulsars can reach spin rates comparable to radio millisecond pulsars, while others pulsate more slowly, their spin rate set by the balance between the accreting material spinning them up and magnetic drag slowing them down. X-ray pulsars are the primary way astronomers study matter under conditions of extreme gravity and density that cannot be replicated in any laboratory on Earth. Gamma-ray pulsars, the newest and most energetically extreme class of pulsar discovered. Neutron stars whose primary emission is in gamma rays, the highest energy form of light rather than radio waves or X-rays. The Fermi Gamma Ray Space Telescope discovered the first confirmed gamma-ray-only pulsar in 2008 and has since found dozens more. What makes them particularly strange is where the gamma rays originate, not from the magnetic poles near the surface as with radio pulsars, but from far above the neutron star in regions of the outer magnetosphere where the physics of emission is still not fully understood. Many gamma-ray pulsars are completely invisible to radio telescopes, meaning they would have gone undiscovered entirely before the era of gamma-ray astronomy. Their existence confirmed that neutron stars can power themselves through mechanisms more varied and complex than the simple lighthouse model first proposed in 1967. Black Widow and redback pulsars, among the most dramatically named objects in astronomy, and the names are earned. Black Widow pulsars are millisecond pulsars whose intense radiation and particle wind are actively destroying their companion star, blasting material from its surface until virtually nothing remains. The companion is reduced to a tiny fraction of its original mass, sometimes less than 1/100th of the sun's mass, and will eventually be consumed entirely. Redback pulsars are similar, but their companions are more massive and not yet close to complete destruction. They are being slowly stripped rather than actively devoured. Both types are thought to represent stages in the recycling process by which millisecond pulsars are created. The companion donated material to spin the pulsar up and is now being destroyed by the very monster he created. It's cosmic irony, written in stellar physics. The double pulsar. In 2003, astronomers discovered the only known system in the universe where two pulsars orbit each other, a binary system called PSR J737-3039A-B, sitting about 2,000 light-years away where both neutron stars are detectable as pulsars simultaneously. The faster one completes 44 rotations per second and orbits its companion once every 2.4 hours, so close that the entire orbital path would fit comfortably inside our sun. This system is the most precise laboratory for testing Einstein's general theory of relativity ever found, confirming its predictions to better than 0.05% accuracy across multiple effects simultaneously: gravitational redshift, orbital decay from gravitational wave emission, the Shapiro delay as pulses travel through curved spacetime. In 2021, a detailed analysis of 15 years of observations produced the most stringent test of general relativity ever conducted, and Einstein passed every single one. The double pulsar is the universe's own physics experiment. The Crab and Vela pulsars, two of the most studied pulsars in the sky, represent the young end of the pulsar family, energetic, fast-spinning objects still embedded in the supernova remnants that created them. The Crab pulsar at the heart of the Crab Nebula spins 30 times per second and powers the entire nebula around it, feeding energy into the glowing gas at such a rate that the nebula has been brightening on one side in recent Hubble observations. The Vela pulsar, born from a supernova about 11,000 years ago, spins about 11 times per second, and periodically experiences sudden spin-up events called glitches, where the rotation rate abruptly increases by a tiny but measurable amount and then gradually relaxes back to near it. These glitches are thought to be caused by the neutron star's internal structure shifting, a brief coupling between a superfluid layer inside the star and its outer crust. Every glitch is a glimpse into the interior of a neutron star, the only way we have of probing matter at densities that no equation of physics can yet fully describe.